class, if you have class second, but second to last or last, you just watch the lesson from home. All right, so.
No, we haven't first.
Okay, and you're screwed. All right, so the last thing we were talking about was parallel circuits, right? And we talked about how you organize the different resistors. Did we get to figuring out voltage in it or not?
Yeah, we just figured out the voltage like equal.
Stays the same. Okay. So we'll just quickly go over it again. So if you have a parallel circuit, real simple one like we were working with the other day, right? Where you have, right, your 3 resistors connected in parallel. Right? We said this one was 3, this one was 2, this one was 1, right? We said the battery was 12 volts, right? We said you have voltmeters, and I won't draw them in, but you have voltmeters over all the resistors and an ammeter after each, right? So you should have that same picture left over from Friday's class. Okay, now, we had said that just like with series circuits, there's those certain rules that we always have to use. Now, our general rule that we can use for both is always Ohm's law, so remember that. Okay, and we had established that voltage, right, that the total voltage is equal to the voltage drop across the first resistor, second resistor, third resistor, etc., etc., etc. Right? So that was our first rule that we established. Now, that leaves us current and equivalent resistance. So we'll work with current first. Okay? What letter do we use to represent current again? Okay, so we want to figure out current. So we need to figure out is it additive, is it equal to itself, what is it, how are we going to do it? Okay, so real easy. Let's look at that first resistor. So I want to find my current through my first resistor. So I want to find I1. Now, I don't have any other information about current, so can I use any sort of I equals this, equals that, equals I, equals that? No, I can't do that. So when I can't use one of the general rules, I have to use Ohm's law. So I can use Ohm's law to figure this out. So if I'm talking about I1, I have to be talking about R and V1. I have to be talking about those values, yes? Do I know R1? What is it? 3 ohms, right? What's V1? What's the voltage across this? 12 volts, right? Because it's the same as the total, yes? So the voltage drop is going to be that. Can you solve for that? Come on, that's the easiest equation in the world. What does it come out to be? 4. 4 what? 4 amps. So I1 equals 4 amps. Cool. Now, our question should be, okay, is my current going to stay constant like it was in a series circuit? Remember, in the series circuit, I1 was equal to I2 was equal to I3. So our logical question should be, so does the same rule apply? Well, how do we figure that out? Let's figure out I2. We know the value of R2. What's the value of R2? We know the value of V2. What's that? And we want I2. Okay? Do we have a formula that connects R, V, and I? We don't have a formula that connects R, V, and I. You're joking. You better be joking. Okay, we got Ohm's law. Use Ohm's law yet again. Okay? Then we're going to get R equals V over I, but we'll make sure we put the proper subscript, so we get R2, V2, and I2. We substitute our values in, and we're going to get 2 ohms is equal to 12 volts over I2. What does it come out to equal? I2 equals 6 amps. Okay, something you should notice about I2 and I1. What are they not? They're not the same. Therefore, in a parallel circuit, what does not stay the same? Current. Current is not constant in a parallel circuit. Right? So IT equals I1 equals I2 equals I3 does not happen in a parallel circuit. Does that make sense? Yes? Cool? Okay, so what the hell is the rule? Well, let's look at this, okay? If we just look at the little piece of the circuit that you can see in the corner here, right? This little piece of the circuit that you can see in the corner here only shows one resistor, right? When I had that one resistor, that 3 ohm resistor, how much current was I pulling out of the battery? How much current was coming out of the battery when I had just the 3 ohm resistor? Right there on the board, you just did the math. 4 amps, yes? The current through the first resistor was the total current, yes? Because there was only one resistor, so there was only one current to speak of. Is everybody following that? Yes? Now, when I add on this second resistor, how much current does that guy pull out of the battery? 6, that's what we just calculated. But he's pulling 6. Does the first resistor give a rat's you-know-what about what he's doing? How much is the first resistor still pulling? Still 4, right? So the two of them, one's pulling 6, one's pulling 4, which means what is the total getting pulled out of the battery? Not volts. What's the total current getting pulled out? If the top resistor is pulling 6 amps and the first resistor is pulling 4 amps, how many total amps are getting pulled out of the battery? 10. How did you figure that out? What incredibly complicated mathematical process did you do? Addition. So you figured out the total current by adding the current pulled from one branch and the current pulled from the other branch. So what do you think our rule should be for current in a parallel circuit? IT should be equal to what? Say it out. Okay, the current, the total current in a parallel circuit is equal to the sum of the current through all the branches. The total current in a parallel circuit is equal to the sum of the current through all of the individual branches. Or if you want to put it in a more formula-y sort of way, like Bouger said, IT equals I1 plus I2 plus I3 dot, dot, dot. Which is very different. So you see how the voltage and the current have flipped from series to parallel? Okay? You see how easily, think about how easily you could screw up a question like this. You guys have all seen multiple choice questions. I guarantee if you have a multiple choice question and it's for a series circuit, one of the answers is using the rule for parallel circuit. If it's for parallel circuit, one of them might be using the rule for series circuit. You have to pay attention to the wording of that question. That's why I give you the quests, so that you can get used to seeing the way that they're put together. Now, if we were to figure it out, right, we could figure out the current through the third resistor, and what would that do to the total value? Make it increase. So the more resistors you add, what happens to the total current you're sucking out of the battery? It increases. You get more and more, right? When I just had 1, it was 4. When I had 2, now it's 10. If I had 3, it would be even more. If I plug something else, then it would be even more, which makes logical sense, right? The more stuff you plug into an extension cord, the more electricity you're going to use. Yes? Right? Now, we've done voltage total. We've done total current. That leaves that one other thing that we always play around with. What's the one other thing that we talked about with series circuits that we haven't talked about with parallel circuits? Resistance. But what kind of resistance? REQ. What does REQ stand for again? What does that stand for again? Equivalent resistance. Remember, it's not total. The reason we call it equivalent resistance is what we're saying is, what if we were to replace all the resistors that were in the circuit with just what? Right? That's what we're talking about with equivalent resistance. Now, if we remember when we originally talked about resistance, we had talked about it as being like electrical friction, right? It impedes the flow of current, right? Slows it down, uses up that voltage, so the current, and then the current can't flow as well and all that stuff, right? Now, in a series circuit, this was real easy. The more resistors you added, the bigger an equivalent resistor would have to be. Why? Because that electron, that charged particle coming out of the battery, would have to go through each one of those resistors in order to make it all the way around. So the more resistors you added, the harder it would be for that charged particle to make it through. So that's why we just did R1 plus R2 plus R3, et cetera, et cetera, et cetera. But let's look at this parallel circuit. We just said something that kind of throws all that for a loop. As we added resistors, what did you start pulling more of? Current. And remember, current is charged particles moving over time. Right? So as I add more resistors, it gives any given charged particle more places to go, which makes it a little bit easier. So the equivalent resistance is not going to be equal to R1 plus R2 plus R3, because that's going to give you a bigger number, and that's going to make your current lower. And we just saw that the more resistors you add, your current actually gets larger. So what the hell does this mean? How do we figure that out? Well, what we realized is that in order to figure out the equivalent resistor, or equivalent resistance, I should say, for a parallel circuit, we're going to have to do a little mathematical gymnastics. When we want to figure out equivalent resistance, the formula we're going to use is this. We're going to reciprocate. We're going to use the reciprocal function, I should say. We're going to flip it. Okay? How does this work? Well, let's find out. So we'll do the example that we're talking about. So what was my first resistor? How many ohms?
3.
What's my second resistor?
2.
What's my third resistor? All right? So there we go. Okay? Now you look at this and you go, oh no. Fractions. Lowest common denominator, because I'm adding them. Oh my God, he's going to make me do this. I hate this man. I wish he would die. Right? And maybe in the back of your head, you remember something I once said. What do we never, ever, ever use in physics? Fractions. We never use fractions. And I said, if you ever get a fraction, what do you have to do to it? Right? It's amazing how much you sound like Viviana, Anthony. Okay? Convert it to decimals. Okay? Do that. How do you do it? Easy. 1 divided by 3. 1 divided by 2. Just turn them into decimals and add them together. It makes your life so much easier. Okay? So what's 1 divided by 3? 1 divided by 2. Everybody. 1.5. 1 divided by 1. Here's the hard one. Okay. Can you add that together? What do you get? 1.83 repeating, right? Yes? But here's the problem. Here's where kids make a mistake. And here's where the test questions are trying to get you. If I actually figure out the equivalent resistance for a parallel circuit with multiple choice, that would be the answer. Choice. Not the right answer choice. Right now, what is that equation on the board telling you? Is it giving you the REQ? What is it giving you? It's giving you the reciprocal. It's saying 1 over REQ equals 1.83. Do I want 1 over REQ? What do I want? REQ. So how do we get rid of it? We reciprocal it. We flip it. We're going to flip 1 over REQ because we want REQ. So we're going to flip that over so we get REQ. Yay! But we have that nasty, annoying problem that happens with algebra, where whatever you do to one side of the equal sign, you have to do to the other side. So we'd have to get 1 over 1.83. Crap, another fraction, but it's cool because it's physics, and we don't keep fractions. So we do the division, and we get an answer of, somebody, with a calculator. Give me an answer. 0.55, like 0.546, right? So it rounds to 0.55 ohms. Yes? That's your answer. If this was a multiple choice question, I can guarantee you one of the choices would have been 1.83, one of the choices would have been 0.55. Because if you don't follow through with the entire equation, you're going to end up with that one spot, and you're going to end up with a mistake. Okay? And that really sucks when that happens because you knew what you were doing, and you just didn't take that extra step. You lost yourself a point where you could have easily had it because you knew what you were doing. Okay? Does that make sense? Now, when you're doing this, the other thing you want to look for, and the reason that you could have also gotten rid of the 1.83, is that there's a rule with the equivalent resistance in a parallel circuit. The equivalent resistance in a parallel circuit must always be lower in magnitude than the smallest resistor in the circuit. I'll say it again. The equivalent resistance in a parallel circuit must always be lower in magnitude than the smallest resistor in the circuit. The equivalent resistance must always be lower in magnitude than the smallest resistor in the circuit. Now that's one of those things that if you remember it, it's a check when you're doing the math. If you were doing this question on a test, and you got to the end of the question and your answer was 1.83, your brain should remember that rule and go, is that right? Is 1.83 a possible answer? Is what? What's the smallest resistor in this circuit? 1, which means your answer would have to be less than 1. Is 1.83 less than 1? No, so you should go, wait a second, either I did something wrong or I missed a step. It's a good way to catch yourself if you can remember that rule. Does that make sense?
Oh, so you're not looking at like the final product.
Yeah, you have to get all the way to the end, so you have to get to that. So if you had stopped here, right, and said, that's my answer, in your brain, you should have gone, wait a second. That, 1.83, is not lower than the smallest resistor, which you already said was 1. So your brain should click and say, I missed something. Make sense? Yeah? Cool. So when we look at this, what we should realize now is that we have a set of rules for our circuits. What is that? What letter is that? Okay, so we have rules for circuits, right? One rule that they all share, that both of them share, is what? What's the one rule or law that they all share? Ohm's law. So you've got R equals V over I. That's both. Series or parallel, both of them can use that formula interchangeably. Cool, no problem. If we look at series circuits, we have our rule. What's our rule with voltage for a series circuit? Somebody. Okay. V1 plus V2 plus V3. Cool. What about current? Same. So I1 equals I2 equals I3. And what's our rule for equivalent resistance? How do we figure out equivalent resistance?
Also, here.
You add them. Right? Cool. Parallel. Yeah. Okay. What's our rule for voltage? We'll do the same order.
They're equal.
They're equal. Okay. Current. And equivalent resistance.
1 over equivalent resistance equals 1 over R over the 1
Okay? Now, the formulas are immensely close to each other. And you can see how easily you can get confused one with the other. So that's why when you're looking at a question, whether it be a part 2 or a multiple choice or whatever it happens to be, you identify, are the resistors connected in series? Are the resistors connected in parallel? Sometimes the wording will say it, sometimes you have to figure it out in the picture. That's why you have the practice questions that you use in the class. Does that make sense?
Yeah.
Yes? Now, one last quick thing, one last general idea that we have to go over. Okay? That last general idea, does everybody have these? Can I go? Cool. And of course, these are all where? Reference table. Okay, nicely listed. Okay, we have what we call the junction rule. Okay? This is called Kirchhoff's junction rule, but we just call it the junction rule. Okay? Okay. Now, the junction rule has to do a lot with like parallel circuits, okay, branching circuits and things like that. And the junction rule has to do with the current going in and out of these branches, okay? So here you have a zoomed in portion of a circuit, right? Remember the other version of the parallel circuits where we said you can kind of branch them out like this, okay? So here you have a zoomed in part. So if this is a circuit diagram, what do all the straight lines represent? Wires. So these are all wires, yes? This circle that you see right here is what we call a junction. Okay? And what do we talk about a junction? Well, a junction is obviously a point where you have some wires coming in and some wires going out. Okay? And obviously what's going to travel along those wires is going to be the current. That's the charge. Now, the easy way to think of a junction is think of the junction like a big train station, like Grand Central or Times Square. Okay? You can take the 7 train or the E train, right? Into Times Square, right? Into Grand Central Station. And you can change and go to the F, to the E, to the 1, the 2, the 3, the N, the Q, the S. Those of you who don't know what I'm talking about really need to start taking some of it. Okay? But you can transfer all these different points, right? Why? Because it's a junction point. It's a point where a bunch of different paths meet and paths go out. Yes? Does everybody understand that? Now, when we talk about a junction in terms of a circuit, what we're talking about is that you're going to have current coming in and current going out. Does that make sense? Yes? Okay? And the rule is it's one way. No backseat. You can't go backwards. We're talking DC, direct current, only going in one direction. Now, Why do we talk about it? Well, because when we talk about current, we talk about a measurable quantity, right? 4 amps, 5 amps, 6 amps, 10 amps, whatever it happens to be. Okay? What the junction rule says is very, very simple. Okay? The junction rule says whatever current goes into a junction, the same amount of current must come out of the junction. Very simple. Whatever current goes into a junction must be equal to the amount of current that comes out of the junction. Simple enough? So if you've looked at the quest, you've seen a couple of these questions, yes? You had no idea what the heck you were looking at. Okay? They're actually really, really easy to do. Okay? So let's say that we had 10 amps going into that junction. A little ammeter on that wire, it measures 10 amps going into the junction. That 10 amps goes into that junction. I put another little ammeter on the top branch. And when I measure that, that one says that there are 6 amps in the top branch. What's in the bottom branch? Come on, everybody.
4 amps.
4. But whatever's on one side of the junction has to be equal to whatever's on the other side. Does that make sense? Yes? Now, this is the simplest of these questions that you're going to see. Sometimes they get a little bit more complicated. You can get a question that looks like this. Okay? What if you got a question like this? Actually, let me flip this. I'm going to flip one of these arrows. Let me flip this arrow. I don't like that arrow that way. Make it a little fun, more fun. Put the arrow that way. Okay? How many junctions do you have in this picture? 2, right? Junction 1 on the top, junction 2 on the bottom. Okay. We'll call this junction 1. Call this junction 2. Okay? How much current do you have going into junction 1? 14 amps, yes? Some for the right, some for the left, yes? Now, that current goes into junction 1, okay? Can it go left or right once it goes into that junction? No, okay? It only has one path. What's the path that that current has to take? It has to go down the wire, yes? So, how much current do you have going into junction 2? 16. Why? Anthony.
This is a wild guess, but because you have current coming from 2 different directions, and there's only one other direction they can come from.
Well, they can go 2, you mean. Okay? So, you've got 16, right? Why? Because you've got the 14 coming down and the 2 coming in, yes? So the total amount going into that one would be 16. 14 down and 2 this way. Which means, what's going to be this mystery place? 16 going out, yes? Does that make sense? Because it's got nowhere else to go?
Oh, so it goes like this.
It goes like
It
this,
bullets
down,
that.
out. Yeah. Okay? Now, in a very simplistic way, this is one of the things that electricians have to figure out. How much current is coming in, how much current is going out. Okay, you have to make sure that the lines and everything can feed and support those things, and that you're getting the current that you're going to need in order for certain things to work. Does that make sense? Yes? Cool? Now, I'm going to give you guys one of those little worksheets that has like the 4 parallel circuit diagrams. You have to figure out the RQs and all those things. Those of you that have done most of the quest, should only have to do a couple of questions in the quest plus the homework. Those of you that have waited until the last possible moment to do the entire quest, you're gonna be in for a fun night. Because you got a lot to do. Okay? We'll go over it tomorrow. Okay? This is the last thing that's on your quest for tonight, so everybody should be good. Cool? Yes? No? Maybe sometimes?
Yes.
Alrighty.
How did you think of the lecture?